So in the last lecture we were thinking about right-angled Artin subgroups of mapping class groups, and now I'd like to present a somewhat more complete theory of right-angled Artin subgroups of right-angled Artin groups, and this is joined with Professor Kim. So we've talked about some bizarre subgroups of right-angled Artin groups and mapping class groups in the previous lectures. So we can add to our zoo of complicated subgroups. So to begin with, so we have gamma. This is a finite simplicial graph. And we'll build the flag complex. So this is a simplicial complex whose one skeleton is just gamma, and then every complete graph on n+1 vertices spans an n simplex. So for example, if we have a graph that looks like this, then the flag complex is a filled-in triangle. So this is topologically a disk. Or if, say, gamma is a square, or say any n cycle with more than 4 vertices, or more than 3 vertices, then the flag complex on gamma is homeomorphic to S1. So now this will be a useful tool for us. So consider the homomorphisms phi defined from they depend on the graph gamma from A of gamma to Z, and they take each vertex V to the generator 1. So for instance, if gamma is labeled like this, we have A, B, C, D, then this map phi of gamma maps A to 1, B to 1, C to 1, and D to 1. So it's not any particular vertex, it's each vertex gets mapped to 1. And it will write K sub gamma for the kernel of phi gamma. So we can think about what this kernel might be in some cases. So for example, if A of gamma is z to the n for some n, then k gamma is abstractly isomorphic to z to the n minus 1. It's like some hyperplane rational hyperplane that you've cut out instead of r to the n. And if A of gamma is some free group, which is not abelian, then k gamma is always going to be some infinitely generated free group. So let's say that a group G is FPN if it admits a classifying space with a finite n skeleton. So what is a classifying space? So that's if you have a group G, then you have, which is so finitely generated, then you have X of G is a topological space with pi 1 of X is just G, and the universal cover is contractible. So a classifying space for, say, K gamma over here, so this is just some free abelian group. This is, you can take X of K of G, can be, for example, S1 to the n minus 1, which has a finite n skeleton in all dimensions. If K gamma is an infinitely generated free group, then you could take X of K gamma to be an infinite wedge of circles, which doesn't have a finite 1 skeleton. And because the fundamental group of X of K gamma is infinitely generated, there's actually no way that you can expect there to be a classifying space with a finite 1 skeleton. So there's a general theorem that makes all these examples systematic, which is due to Bestvina and Brady, and it says that K gamma is FPN if and only if for all I less than or equal to n, pi I of f of gamma is trivial. So this is for including I equals 0. So let's think about this this for a second. So in the case where A of gamma is Fn, then the defining graph is a disconnected graph with n vertices. And so its pi 0 is not connected. So did I get the indices wrong? So Fp. Oh right, yeah. So pi 0 is not trivial. And so yeah, I'm sorry. So this should be n minus 1. Okay, there we go. So pi 0 of a completely disconnected graph on more than one vertex is not trivial, and therefore, if we look at the flag complex doesn't have a trivial pi 0, and so then therefore you're not supposed to have FP1, and so that means that that K gamma cannot be finitely generated. Similarly, in this case, we had a cycle on 4 or more vertices, then the flag complex is homeomorphic to S1, which has trivial pi 0 but non-trivial pi 1. And so the theorem implies that the kernel K gamma for gamma, this cycle, is going to be FP1 but not FP2, so that it's finitely generated but not finitely presented. And the one more example here, if we have a complete graph on any number of vertices, then the flag complex is contractible. And so all of its pi i's vanish in all dimensions, and so you have FPN for all in all dimensions. And so we see that from this example here, that xk gamma in the case of a complete graph can always be just taken to be a product of circles. Okay. So these are some fairly bizarre subgroups of right-angled Artin groups. And I'll just recall some other subgroups that we had. So if n is greater than or equal to 5, then there exists a closed surface of genus G greater than or equal to 2, such that, let's say closed surface S, such that pi 1 of S embeds in A of Cn, so inside of the Artin group on the cycle of length n. And so this was a theorem of Drom's. And more strikingly, recall that we mentioned if G is the fundamental group of a hyperbolic 3-manifold, of finite volume, then there exists a finite index subgroup G prime and a graph gamma such that G prime embeds in A of gamma. And this is due to Agel. And so now we'd like to say what are sort of the right-angled Artin subgroups, the more nicely behaved subgroups of right-angled Artin groups. So we begin by defining the extension graph. So this is defined by, the vertices of gamma E are given by V to the G. So this is a conjugate of V by G, where V is a vertex of gamma and G is an element of the right-angled Artin group. So the vertices being generators of the right-angled Artin group are elements of the right-angled Artin group, and the right-angled Artin group acts on itself by conjugation. And so we can define this. And the edges of gamma E are basically the same thing. So conjugates of edges, where we view it as such, where an edge is a pair of vertices, and an e to the g is just the conjugate via the diagonal action. Okay, so one sort of direction of the sort of classification of right-angled subgroups of right-angled Artin groups is the following. So if lambda sits inside of gamma e, this is a finite induced subgraph, where by induced I mean I take the vertices that lie in lambda and I have to include all edges that are included in gamma e, then A of lambda embeds in A of gamma as a subgroup. So I'd like to state a converse. But before I do that, I have to define one more object. So what we need is the click graph. Gamma ek. So this is, a click graph is one name for it. It's not particularly standard. It's some sort of a barycentric subdivision, but let me just define it. You can define this for any graph, really. So lambda is any graph. And then you can define lambda k as follows. So if C inside of lambda is a complete graph on any n at least one vertices, we include V sub c in the vertex set of lambda k. And V sub c is connected to V sub c prime if and only if C union C prime span a complete subgraph. Of lambda, of course. So this is the definition of lambda k. So just to give you a little bit of a feel for what this looks, it looks a lot like lambda, especially when lambda is big. So first of all, lambda k contains lambda itself, because I said that we add this these vertices, one for each each complete subgraph on at least one vertex. So in the case where n is equal to 1, we just include the vertices of lambda. And so then what sorts of extra vertices do we get? Well, if this was an edge inside of lambda, then we get a vertex VAB corresponding to this edge. And now, so you can sort of label this by the subgraph spanned by A and B. And now VAB has some edges coming out of it. A and B together with A span a complete subgraph, and so we get an edge here. A and B together with B span a complete subgraph, and so we get an edge here. And now it's possible that A and B have a common neighbor. And so then A, B, and whatever this vertex here is, also spans a complete subgraph, and so we get an edge right there. And so that's sort of an idea of what this looks like. So we can now, equipped with this terminology of the click graph, we can state this theorem fully. And so the theorem is if A of lambda sits inside of A of gamma as a subgroup, then lambda embeds in gamma ek as a subgraph. So observe that this is not an if and only if characterization of subgroups of right-angled Artin groups, which are themselves right-angled Artin groups. And one could hope that you could just remove that k from gamma ek. But unfortunately, that's not true. And as we just found out today, actually, we were sent a preprint by this is a theorem of Casals, Duncan, Kazuchov. I think that's spelled correctly. So it says that there exist embeddings of right-angled Artin groups A of lambda into A of gamma such that lambda does not embed in any way in gamma E. So this is the strongest that you could possibly hope for. There is a there is a corollary to this, which does allow us actually to get rid of the k. So I'll write it as a corollary, but it's not that straightforward. But so if gamma is triangle free, then A of lambda embeds in A of gamma if and only if lambda embeds in gamma E. So then this theorem here of Casals, Duncan, Kazuchov would have to be for graphs which have triangles in them. So you're allowed to do some sort of, you have to do something with commuting generators, assuming that both of these theorems are correct. And so I'll give some motivation for why we would care about a theorem like this. So the motivation comes from actually understanding closed surface subgroups of right-angled Artin groups. So we had this theorem that I wrote down, but I've erased already, that you have pi 1 of some closed surface group sitting inside of A of Cn for all n greater than or equal to 5. And so, because we know that these Artin groups on long cycles, so by long I mean n greater than or equal to 5, all contain closed surface groups, one place to look for closed surface groups instead of right-angled Artin groups is from copies of Artin groups on long cycles. And so this theorem gives us a tool for finding such subgroups. And so what one can then show is that if gamma is triangle free and A of Cn embeds inside of A of gamma for some n greater than or equal to 5, then we have some Cm sitting inside of gamma for some m greater than or equal to 5. This m and this n might not be the same, is the point. But if you can find a Narton group on a long cycle, the point is that it has to come from a cycle that you already, well, that means that you could already see one inside of the original graph. And this, the conjecture that I'm about to state, or what was formerly a conjecture, was sort of the motivation behind all this work, was that the conjecture, as it was originally stated, said that A of Cn embeds in A of gamma if and only if some Cm is inside of gamma, where now gamma had no hypotheses on it, including triangle free. And so this was proved to be false by, well, this is false by a theorem of Professor Kim. Kim showed that if we take the graph C6 bar, which looks like this, so it's like this envelope or a triangular prism, then one sees that there are no long cycles in this graph which are induced. If you draw a cycle which has length 5 or 6, then it always contains an edge that you wouldn't want to be there. And what was shown was that A of C5 embeds in A of C6 bar. And so then this conjecture as it stood had to be revised a little bit. So what one can show, in fact, is that if you take C6 bar and you compute its extension graph as we had here, then one can show that the extension graph actually contains a copy of C5. And so you can see why one way in which this is true from looking at the extension graph. So let me just write that down. So C6 bar E contains C5. And so the conjecture as it stood here was then revised to say that either Cm is contained in gamma or Cm bar is contained in gamma for some m. So there are some further complicated examples that can be described. There was a paper of Crisp, Sagiv, and Sapir, which took all graphs with at most 9 vertices and determined which A of gammas have closed surface groups, subgroups. And sort of the surprising examples were, if we take the path on six vertices and take its complement, or we take the path on 7 vertices and take its complement. Well, I'll draw one of these. These all contain surface right-angled Artin groups. They contain closed surface groups. So this here is P6 bar, and these contain closed surface groups. And so the question is, then, do these actually contain right-angled Artin groups on long cycles? So can you conclude something like that? And so if they don't contain Artin groups on long cycles, then you've produced new examples of surface subgroups of right-angled Artin groups that don't come from Artin groups on long cycles. So what was shown by Crisp, Sapir, and Sagiv is that A of P6 bar does not contain A of Cn for n odd. And so it may contain A of C6 for all we know. Now, if we compute the extension graph of P6 bar, P6 bar E has no long cycles. But since P6 bar has triangles in it, then we can't apply our triangle-free theorem here. And so we have to pass to the clique graph. But P6 bar E, P6 bar E, K does have long cycles. And so we're out of luck. However, this has recently been resolved again by these 3 authors. They proved that A of C5 embeds in A of P7 bar. And so this conjecture turns out to be completely wrong. It was a good try. But yeah, that's where some of the motivation for this theorem came from. So now let me tell you about some aspects of the proof of the theorem. So now that we have all that down, so I'm going to break the theorem into 2 pieces. And prove them separately. So the first part of the theorem is if you have a finite induced subgraph of the extension graph, then you get an inclusion of right-angled Artin groups, and the second one is the converse. So first I'd like to talk about the proof of the first part. So before we do that, it would be helpful to have a better, sort of less abstract understanding of what the extension graph really is. So how can we build the extension graph? Explicitly. So here's sort of one construction, as if you have the graph gamma and you take another copy and you have a vertex here, V, and these are all the vertices which are adjacent to V. So this is all the star of V. You can take the other copy of V and its star and the other copy of gamma, and then you can glue them together. And so you get, here's the star of V, and here's V in the middle. Okay, so what does this give us? Well, really this gives us a piece of the extension graph. And why is that? You can think of this graph here as gamma, and then you can think of this other copy of gamma over here as gamma conjugated by V, viewed as an element of the right-angled Artin group. So the conjugation action commutes with everything in the star of V and with nothing else. And so the vertices outside of the star of V are conjugates of the corresponding elements in the original copy of gamma by conjugates by V, and then everything in the star is fixed by the conjugation action. And so what one can do is one can repeat a sort of doubling over stars of vertices over and over. And so if you take, one has to be a little bit careful when defining this correctly, is that if you take a union of doubles of gamma over stars of vertices, then you get gamma E. And so really to prove one, the first part of the theorem, all you have to prove is that if you have a finite subgraph of gamma doubled along the star of some vertex with itself, then you get an inclusion of right-angled Artin groups. And so how can you do that? Well, I'm going to use the theorem that we discussed last time. I'll use a special case of it, actually. So recall that we had this if T1 to Tk are Dane twists about distinct simple closed curves, then for all n sufficiently large, and we have T1 to the n all the way to Tk to the n, generate a subgroup isomorphic to A of gamma, where gamma is the coincidence graph. Of the supports. Okay, so what can we do with this? Well, given gamma, choose a surface and twists T1 to Tk with coincidence graph gamma. And so, I don't know what this looks like. There are some curves like this. Something like that. And now, what's a vertex V? Well, it's a power of one of these Dane twists. So let's say it's a power of the Dane twist about the blue curve. This is V. And now, what's the result of conjugating T1 by V all the way to TK by V, or even doing T1 to the N conjugated by V all the way to TK to the N conjugated by V? Not that it matters which do we do first. Well, conjugating by V is the same as applying a high power of the Dane twist about this curve to the support. It's this general fact that is, if you're not familiar with it, is a good exercise that if we have any F in the mapping class group and gamma is a simple closed curve, then T gamma conjugated by F is equal to T of F of gamma, or F inverse of gamma, depending on your convention with in which order you write F and F inverse when you conjugate. And so, observe now that this Dane twist will commute with another Dane twist precisely when the supports are disjoint, which is precisely when in the coincidence graph the two corresponding vertices are adjacent to each other. So that means that that conjugation by V fixes precisely the vertices which are in the star of V. So that implies that the coincidence graph of the maps of the Dane twists T1 to the N, TK to the N, T1 to the N conjugated by V, TK to the N, conjugated by V, is gamma union gamma over the star of V. Yes?
I have a question. Power of V means that power of Dane twist of V.
Sorry, so V is already a power of a Dane twist. V is equal to Ti to the N for some I on this list. And so if we apply this theorem now, that means that T1 to the N, maybe to some higher power M, all the way to TK to the N, taken to some further power M, and then T1 to the N conjugated by V taken to some higher power N, and then all the way to TK to the N conjugated by V taken to some higher power M. These generate a right-angled Artin group. Isomorphic to this one. And therefore, we've shown what I've claimed to show over there. And so this establishes the first part of the theorem. Okay, so now I want to keep the statement of the theorem up here. So I'd like to give a proof of the second part.
Question.
Yes.
why A gamma in your star gamma is in A gamma?
Oh, because these elements were in A of gamma, and I've taken these conjugates which are also in A of gamma, and then I take them to powers. So I'm doing multiplication within A of gamma, and so this is actually, yeah, contained in A of gamma. Okay, so now the proof of part 2 is somewhat more involved. So the issue now is that if I give you, so I have some map now, A of lambda to A of gamma, and so say a vertex Vi here is mapped to some element Wi in A of gamma. But if I started with some arbitrary collection W1 to Wm, and I asked you what's the subgroup generated by these elements, I mean, in general, unless I know that it's actually the image of some injective map between two right-angled Artin groups, I have no idea what this isomorphism class is. And so the difficulty is basically the following. So we build the commutation graph, which I'll write C of this collection W1 to Wm, and whose vertices are W1 to Wm, and edges are commutation. So Wi is connected to Wj if and only if Wi and Wj commute. And so the difficulty that one has to overcome is showing that the commutation graph of W1 to Wm embeds in gamma ek. So once one can show this, one is essentially done with proving the theorem, since once you have an injective map, I mean, these vertices might not be sent to conjugates of vertices or even products of commuting conjugates of vertices or anything, but you're handed a bunch of words whose commutation graph is lambda, because that's the commutation graph of the vertices, and this map is injective. And so you build a commutation graph of some collection of elements, and if you can show that that graph actually embeds in the click graph of the extension graph, then you've proved part 2. So how might we do that? Well, I'm going to simplify the situation just a little bit more and then show what has to be done. So it's possible that if I give you some element W in A of gamma, which is not the identity, then you might be able to write W as a product W1 times W2, where these commute with each other, and where they're both not the identity. Also, they shouldn't be proper powers of each other. So And furthermore, that their lengths, sort of they're in the word metric, so the shortest expression in the generators of A of gamma that's needed to express them is strictly shorter than the length of W. And so what one can do, so if you can't write W in such a way, if W cannot be decomposed like this, then W is pure. And so if you start with any word W, then you can always ask, is it pure? And then if the answer is yes, then you're done. And if the answer is no, then you write it as W1 times W2. And then you take W1 and you ask, is it pure? And then you sort of have this flow chart. And what can be shown is that this process of writing W as a product of pure elements will terminate in finitely many steps. And so what I can now assume then, what has to do a little bit of work to show that this is enough to prove the theorem, is that if W1 to Wm are pure, then the commutation graph of W1 to Wm embeds in gamma E. So I'd like to sort of sketch the proof of this in the time that remains. So the proof starts the same way as the first part. So you have this collection T1 to Tk of Dane twists with coincidence graph gamma. And now what you can start with some Wi on our list, and first cyclically reduce it. So that means you've conjugated so that if you have a vertex and its inverse occurring at the beginning, at the end of the word, you just get rid of those. It's really just a conjugate of Wi. And now Wi is some product of vertices in the graph. So the way I've written this, these vertices don't necessarily commute with each other. There may be a lot of repeats. There may be some inverses, so on. But these vertices correspond, each Vi, well, let's not use Vi, Vj corresponds to some Dane twist Tj about a curve gamma j. Now, sort of the fundamental observation is that if Wi is pure, then the curves that we have here, gamma 1 union gamma 2 all the way to gamma k, fill a connected surface. So recall what that means. I draw these curves on my surface and I take a tubular neighborhood of them. So a neighborhood of gamma 1 all the way to gamma k, and then I cap off any contractible disks that I might get, so I fill those in. And the point is that this is a surface Si contained in S, because remember I'm doing all these Dane twists on a fixed surface, which is connected. Okay, so now I have, for each of my pure elements, I've built you a subsurface of my original surface. And now observe that the coincidence graph of the subsurfaces that I've produced for my words W1 to Wm, of S1 to Sm, is the commutation graph of the words W1 to Wm. And so now what can you do? Well, observe that I have these vertex generators, which are Dane twists on these subsurfaces Si. And so this step requires a little bit of some facts about the mapping class groups, and so I'm not going to belabor that point. So maybe it's just best if you don't know about these facts to just sort of not worry about them. So there exists a product of the Dane twists what did I call them? T1 to Tk on the surface Si, such that, so call that product psi, such that psi is pseudo-Anosov. And this remains true if I take any powers here. So I can assume that these powers of these Dane twists are actually my vertices, or some vertices of the graph gamma. And so now I'll label this pseudo-Anosov by I because it's on the ith subsurface. And now take one of these curves about which I'm twisting. So gamma j here sits inside of Si, and if I take a sufficiently high power here, psi I to the m, and I apply it to gamma j, then this quote-unquote fills up the surface. So it doesn't fill up the surface in the sense that it doesn't cut it up into disks, because gamma j and all its homeomorphic images are simple closed curves. But the point is that if C intersects Si, if there's any simple closed curve, then for all m sufficiently large, we have psi I to the m applied to gamma j intersects C. Okay, so now we're almost done, because if we just take one such curve, gamma sub j, on each surface Si, and we apply this sufficiently high power of a pseudo-Anosov, then we get a configuration of curves which has the exact coincidence correspondence of this. So this is just sort of an exercise really in imagining what this looks like. So I'll just label this gamma j by an I so that we remember which subsurface it came from. And so then the coincidence graph of these curves, psi 1 to the m of gamma j1 all the way to psi little m to the big M of gamma j little m. This is equal to the commutation graph of W1 to Wm. And now since this pseudo-Anosov is viewed as an element of the right-angled Artin group, and applying it to a curve is the same as conjugating the corresponding vertex generator of the Artin group by that element, then these elements, these curves, are the supports of Dane twists, which are elements of the right-angled Artin group itself. And so these curves are viewed really as vertices of the extension graph of gamma. And so that implies that the commutation graph of W1 to Wm actually sits inside of the extension graph. And that's how the proof goes. So it's a good place to stop, I think.